Hello, welcome back. In this segment, I will briefly talk about format preserving encryption, which is quite a fascinating idea. The goal is to encrypt piece of data, but preserve the structural properties. For example, you may have a credit card number and you would like to encrypt, but you don't want to have longer output, meaning you want it to fit in your current database schema. You want it to not change the data model, whatever you have. So you wanted to preserve length, you wanted to preserve structural properties like made of numbers, made of characters and so on, special characters. So you can restrict the output into the set that you would like to have. That's the idea of format preserving encryption, which has many interesting use cases in legacy systems context, because you don't want it to change the database models, database schema, whatever. And it's also important in the context of interoperability. Maybe you have two systems that have to work together. And if you encrypt one of the data, then the problem is that the data will have longer output. The encrypted data will have a longer output than the input, and it may break interoperability with your backend systems and whatever. Okay, so the idea of this segment is to talk about format preserving encryption. In particular, I will take one structural property. Suppose you would like to preserve the length constraint. Let's say you have a number which is secret. It would only require, say, 120 bit. Okay. But if you call AES, it will very likely give you 128 bit as an output, which I will show to you now very quickly. Java Aes Demo. Okay, I need to put some text. Let's say I put the text like this. How many bytes are there? You have to count this as a character, not a number. So 10 plus 5, 15 bytes. You see here, the output is 16 byte, although the input is 15 bytes. That means the regular AES algorithm would not preserve the length. We can overcome this limitation by using this idea of format preserving encryption. So if you look into this Wikipedia, there are a lot of interesting references mentioned in here. And I'm going to talk about one algorithm. This algorithm is not necessarily scalable and not necessarily applicable everywhere. So just take it as a introductory material, okay? So the idea is pretty novel in this cycle walking context. You have some ciphertext, they call it X, and you apply AES. In this case, whenever they say P, you can imagine as AES. Cryptographers use permutation instead of a concrete implementation like AES. Okay, P of X is one implementation now. You can imagine AES. Okay, we check whether output of AES is an element of M. What is M then? M is the desired set of values. Okay, maybe all possible, in my case, all possible 120-bit numbers, perfectly fine. So I check whether the output of AES is an element of M. If it is, then I terminate the recursion. Otherwise, I encrypt it again until the output reaches an element of M. Okay. All right. So we can visualize it more clearly how this works. I have this diagram which has all possible 128-bit numbers. Okay. That means there are 2 power 128 possible numbers. I place it here. Okay. But my message, my message space is only say 120-bit numbers. Okay, that means what is the size of this? This in terms of size, it is 2 power 120 numbers, right? Okay, the area is not necessarily scalable, so just to focus on the concept rather than the diagram's clarity. Okay, so the inner circle that I have drawn, or something like a circle, is my desired set. Okay, this is the allowed set of values. Okay, so let's say my plain text is a member of this particular set. Okay, here is my plain text. If I encrypt it, it's very likely that I jump out of my inner circle and I'll come here. Okay, so here is my first ciphertext. But that ciphertext is not good for me because it's not 120-bit anymore, right? It could be 128 or 127, whatever. So I keep on encrypting. Maybe I'm here. I keep encrypting until my output suddenly comes here back. Okay, so if it comes to my inner circle, then I know for sure that my output length is a right length. Okay, 120-bit only. So that's the encryption part. So basically keep on calling AES until it comes to that desired set of values. How about decryption? Well, decryption is just opposite. You know the final output, that's the output that you're here. So you keep on take your steps backwards until the AES output gets back into the allowed set of values. Meaning, if you get an output which is 120 bit, then you know for sure you reached the input. So this is my input, plain text P or X to be consistent. This is my plain text X, right? And I keep on calling AES, so I get my ciphertext. And in the reverse, I keep on decrypting until the decrypted result is back to my allowed set of values. Okay, that's the idea of this cycle walking, which I have implemented as a proof of concept. Now I'll talk about that. Implementation 120, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5. So I have only 15 bytes. Let's see whether we can get an output, which is also 15 bytes. Yeah, you see here, I got an output, which is also 15 bytes. Now let me explain what is this number of steps, meaning 489. Remember, I drew a picture on my whiteboard. Here is my collection of 2 power 128 possible numbers, and here is my allowed list, which is all 120-bit numbers. So my plain text is a member here because it has only 120-bit in terms of bit count. So how many steps I have to do, meaning how many times I have to call AES until the final ciphertext comes back here to the allowed set. 489 times I have to call, which is slightly above the expected value, right? I mentioned to you the expected value should be only 256. It's difficult to predict exactly. I mean, it's probability, right? We're predicting expected values. Okay, so let's now continue one more time and see whether we get the number of steps more or less. Okay, in this attempt we got an output which is only in 199 steps. Okay. You may wonder, why am I getting a different ciphertext every time? The reason is that inside my cycle format preserving algorithm implementation, I generate a new key. Otherwise, AES is a deterministic function. You know, it will always produce the same output for the same input because it's just only one block. Just to be clear, not to confuse with cipher modes. Cipher modes help you to encrypt more than one block, and thereby they introduce randomness using IV, nonce, and so on. But if you have only one block, there is no randomness in AES. AES is just a deterministic function. Okay, that's the reason why you would get same value. But in this case, you're getting different value because I'm changing the key inside my cycle format preserving algorithm. Okay, all right. So you get the idea that by keep on calling AES, you can get an output to the desired list, but the number of steps is enormous, as you can see already. Just to reduce an output, or just to work in 120-bit instead of 128-bit, I have to call AES 339 times. That's very inefficient. But I will show you more. What about now? Just basically 112-bit number. Let's see how many times I have to call this. Oh my goodness! You can see here it has to call AES 95,000 times approximately. Okay, which is enormous, and it's really slow. So the algorithm that is discussed here on the Wikipedia page is an interesting algorithm for sure, but it has its limitations in terms of if the desired EM is so small in the set of all possible outcome, then this cycle walking is very inefficient. Okay, you will not be able to use it in practice. It is useful if EM is as closest to the size of the original space. But if EM is very, very, very small, then, like for example, if you want only a 10-bit number from AES, you have to call it enormous number of times. Okay, that's not efficient. Okay, but if the size of the desired output is so close to 128-bit, then of course, yes, this algorithm works, and we have checked it. Okay, so that's basically it, and I will very briefly now show to you how I implemented this algorithm. Right? Maybe you're interested in replicating yourself, so I'll show that. Okay, what I do here is you have to pass a plain text string as an argument, right? And then I convert your plain text into bytes, right? Okay, and then here is the important point. My desired set is set of all numbers that are smaller than or equal to the size of the input. That's the reason why I say take the input length, and the reasoning behind this line is as follows, right? I wanted to have my ciphertext number smaller than or equal to 2 power 120. For example, if the input is a 15-byte number, 15 byte means 120 bits, and I will definitely like to have an output also 120-bit number. That's the constraint I'm putting in here. Okay, that's the max value as an integer. And I'm passing the max value for my permutation cycle. And I will explain to you how the cycle permutation works. The cycle permutation keeps calling AES in the loop, like a permute means AES is called under the hood. And it checks whether is the permuted value smaller than or equal to the max value. Okay, if it is true, then we break it, meaning we know we reached the desired set of values. Otherwise, we keep on continuing this. Okay, and the incursion will stop, but it will take very long time depending on what type of value that you are restricting to. Okay, so here is the permute, which is just AES. And just to make a clear note that although it shows AES ECB, there is nothing wrong in using ECB in this context, because I have a unique message that I'm encrypting and I have only one block. If you have only one block, there is no reason to use IB, nonce, or whatever, right? That's the reason I'm putting it here. Okay, that's basically it. I hope you got the idea of the format preserving encryption. One specific algorithm we discussed is how to preserve the length. The important message is that if the output you are looking for, the length of the output in particular, is close to the length of AES output, then this algorithm works. But if the output that you're looking for is very, very small in comparison to the output of AES in terms of the bit size, then this is not a scalable algorithm. So I'll talk later about other algorithms. Okay, for now, this is good enough.